Okay, this is lecture 2.1 on the rectangular coordinates and graphs. I realize most of you are preparing for the exam and you may actually look at this after the exam, and that's fine. This is the only lecture for this week, and most of this should be familiar to you. So the rectangular coordinate system is made up of two axes. The one that is horizontal is called the x-axis, and the vertical one is the y-axis. You can think of the x-axis as the regular number line. At the start, at the 0 point of the number line, we place a perpendicular axis called the y-axis. Positive numbers are to the right on the x-axis and above the x-axis on the y-axis. The point right in the center is called the origin. A particular point is represented by an ordered pair. You find its address. Each ordered pair has an x address and a y address. So this ordered pair, if I drop a perpendicular down to the x-axis and I count over at the origin, 1, 2, 3, so I get the x value. For the y value, I go either to the right or to the left, wherever the point is located, perpendicular, and when it intersects the y-axis, I grab that value, and it's the second coordinate. So an ordered pair is a pair of real numbers enclosed in parentheses. These are not intervals. They are two-dimensional points. Although they look like intervals. They're separated by a comma, and this is the general way we refer to them, x comma y, because the first number x refers to its position hovering over or below the x-axis, and y refers to its position to the right or to the left of the y-axis. So the first number is called the x-coordinate. Sometimes I'll call it the first slot. And the second number is called the y-coordinate. Sometimes I'll call it the second slot. Note that two ordered pairs are equal if and only if both numbers in each ordered pair are the same and occur in the same order. So 1/7 is equal to 11 divided by 11, because 11 divided by 11 is 1, and 7 is equal to 7. But 1/7 is not equal to 7/1, even though the numbers are the same, they're not in the same order. So ordered pairs, unlike sets, the order matters. So that's something else to just keep it in the back of your mind. So a point is a one-dimensional object in the rectangular coordinate system whose location is given by an ordered pair. One-dimensional means it has 0 width and 0 length. The point 0, 0, right at the intersection of the x and the y-axis, graphically indicates the intersection of the x and the y-axis. The x-axis is the set of all ordered pairs in the rectangular coordinate system whose y-coordinate is 0. In set notation, it's the set of ordered pairs x, y, such that y is equal to 0. We have a similar definition for the y-axis. You don't have to memorize these, but it is a technical definition. It's the set of all ordered pairs in the rectangular coordinate system whose x-coordinate is 0. In set notation, it's the set of ordered pairs x, y such that x is equal to 0. You can just think visually about it. Although sometimes these definitions are helpful, because if a point lies on the x-axis, then its y-coordinate will be 0. If a point lies on the y-axis, then its x-coordinate will be 0. Quadrant, we use these sometimes to refer to different parts of the coordinate axis. But there they are numbered. You start in quadrant 1, then go counterclockwise to 2, 3, and 4. Notice that the quadrants do not include their boundaries. So this point here, 3, 5, is completely in quadrant 1. But the point here, 5, comma 0, 0, it's straddling quadrant 1 and 4, and we don't need to say it lies on the x-axis. So points are either in quadrant 1, 2, 3, or 4. They lie on the x-axis, or they lie on the y-axis, or they lie on both, and there's only one point for which this is true, and that's the origin at 0, comma 0. So one of the nice things about the coordinate system is we can let the axes designate different values. In this particular case, we have a category: food, housing, transportation, healthcare, apparel and services, entertainment, and an amount spent in each category. And we can literally use this table to write ordered pairs that express the relationship. So those ordered pairs will look this way. It's just a different interpretation of an ordered pair. So normally we have ordered pairs. We talk a lot about dimensionality in mathematics, and you've just entered the world of two dimensions. So the normal ordered pair is x, y, and x is a number and y is a number. Here we're going to have something different. We're going to have category and then amount. So using that designation, I would have food, and the amount would be 8,506. That's a different type of an ordered pairing. Housing, 21,374. Now, they introduce this example and then they pretty much leave it alone. These types of categorizations are something that are important in statistics and different ways to categorize data. For us, we are never going to have something in the first slot that is not a real number. So this is just a kind of an FYI. This also happens, and that's it. That's all there is. I don't think there's anything else in this particular section that makes use of that. I actually find it rather odd that it suddenly appears literally at that example rather than at the very last of the chapter when it says, by the way, we could do this. So anyway, there it is. So here is the cool thing. We have, here is the rectangular coordinate system. And I'm going to put a point here and another point here. And the interesting question is each one of these points having a coordinates. If you come over here, you can see the coordinate of point A. It's 2.7, comma 3.74. Those are approximations. And coordinate B is minus 9.26, comma minus 2.26. So point A is in quadrant 1, and point B is in quadrant 3. So what we would like to know is what is the distance between these points. So I just drew a line, and in mathematics the concept of distance is almost always equivalent to the shortest route between two points given the underlying geometry. And our geometry here is just a flat sheet of paper. It's not spherical, it's not convex, it's just a flat sheet of paper. So when we have the real line, so when we have a point at 7, to find its distance, we literally just take and measure the distance between 0 and 7, and we get 7. So we already have this concept of distance between two numbers. Equivalently, if I were down here at minus 7, I don't know if I'm exactly getting the minuses, its distance is the absolute value, but its distance again is 7. So we have this concept of distance. So when we're in just one dimension, so one dimension is just the real line. Why is it one dimension? Because you really only have one choice. You can go forward or reverse forward. 2 dimensions, I could go forward or reverse forward, which is backwards, or up or reverse up, which is down. But in one dimension, just the regular number line, the distance between two numbers, p and q, is given by the absolute value of p minus q. And it doesn't matter which order it is. So if I want to know the distance between 7 and 21, I can subtract 7 from 21 and take its absolute value, or 21 from 7 and take its absolute value. One of those will be negative and the other will be positive, and the absolute value doesn't do anything. But we also have a distance formula for 2 dimensions. And let's actually derive that. This is the distance formula. So let me do that here for you. It needs to be derived. I mean, I could just give it to you, and some of you really don't care about its derivation, but this is math, so we're going to derive it, because otherwise, why should you take our word for it? So I'm going to say that this is some arbitrary point. So it's going to have an x value, which I'm going to call x sub 1, and a y value, which I'm going to call y sub 1. And I'm going to put another coordinate down here, another point down here. I don't know what it is, but it's going to have x2 value and a y2 value. So what I want to know, what I want to find out, is the distance. If I travel along this straight line, how long is this line? So what we do is we take note, we kind of draw a right triangle. Now here I'm going to go ahead and erase the overlap here. Maybe. Yeah, there we go. So this is a right triangle. And you already know that since this is a right triangle, and we can denote as a right triangle, it's customary to put a little bitty square right there. And when it has that square, it tells you it's a right triangle. We know if this is length A and this is length B, then A squared plus B squared is equal to C squared, where C is that length. Now I need a square there. But that's A squared plus B squared gives me the distance times itself. So if I want to know just the value of C, then I take the square root of both sides. And remember, when I take the square root of C squared, I just get C, and it's a positive value, because if I want the negative root, I would put a negative here. When I don't have a negative here, this is assumed to be a positive value. So now all we need to know is, how do we calculate the length of B? Well, supposedly this is in some coordinate axis. So I'm going to draw the coordinate axis here. And, well, really, I'm not even going to bother to do that. Notice that this point here is at y1 above or below, we'll say above the y-axis, and below it is y2. So the absolute value of y1 minus y2 is equal to my b value. The same over here. if I subtract my x1 value from my x2 value in absolute value, then I have my a value. But you know the cool thing about this is when I square the absolute value of y1 minus y2, I always get a positive number. So when I take b squared, which is equal to the absolute value of y1 minus y2 squared, that happens to be just the same as y1 minus y2 squared. When I square a, it's the absolute value of x1 minus x2 squared. But since this is always positive, and any negative number times itself is a positive, and any positive number times itself is a positive, this is just the same as x1 minus x2 squared. So if we call this down here point P, and we call this up here point Q, we now have the following formula. And we're going to denote the distance between P and Q by a D, P, comma, Q. That's just read as the distance between points P and Q. That's what that's read as. So it's equal to the square root. Well, what did we decide a squared was? It is x1 minus x2 squared. Plus, and what did we decide b squared is? y1 minus y2 squared. All of this is under the radical. So we're going to be taking square roots. So let's go back and see what so this is our distance formula right here. The distance between 2 points P and Q is the difference in their x coordinates squared plus the difference in their y coordinates squared. And the order here is not important. x1 minus x2 squared is the same as x2 minus x1 squared. And similarly on the other side. So let's go back and let's use the distance formula to find the distance between these 2 points. It was minimized. Well, that did it anyway. So we'll kind of keep our distance formula over here. And if that bothers you, I learned a new skill. I can literally straighten it up. So our point P is given. P is given by the coordinates minus 8 and 4. So we will let that be x1 and y1. It does not matter. You could have put x2 and y2. It doesn't matter. And then our point Q is given by 3 minus 2. And that will be x2 and y2. Now it's just plug and chug. The distance between P and Q is equal to, write your big, huge square root symbol. x1 minus x2. So minus 8. Notice here the minus signs are inherent. So that means they're there. If x2 is itself negative, it has to bring that negative along with it. So minus 8 minus x2 is 3. We're going to be squaring that. And then we're going to add y1 minus y2. And here the minus 2 has to bring its negative with it. It can't use the one that's already there. So now we're just going to do simplifications. So minus 8 minus 3 is minus 11 squared. And 4 minus a minus 2 is 4 plus 2, and that's 6 squared. So we've got a lot to do here. So minus 11 squared is minus 11 times minus 11. That's 121. And 6 squared is 36. So this is equal to the square root of 157. And 157 can't be factored. That's it. And this is the answer we want. Just this. So here is the thing. In this class, and when we were tested on this, answers should be given in exact form. This is exact. The square root of 157 is exact. What I don't want you to do is bring up a calculator, hit the square root sign, hit in 157, and hit equal, and write down 12.52996480046. That's not what I want. I want the square root of 157. This is an approximation. The square root of 157 is exact. If you need an approximation, then the exam will tell you to use a calculator. So we'll cross that. We'll cross that pond or river or whatever you want to call it when we get here. So here is an interesting application. We have two interesting applications of the distance formula, and I'm going to do something here. I'm actually going to want to use this particular graph. So I'm going to copy this entire thing, come back over here, and hit new canvas, and do layer, paste from clipboard, and that allows me to do the writing. So now I can just maximize this, and we're good to go. So we want to determine whether the points m minus 2, 5, n 12, 13, and q 10, minus 11 are vertices of a right triangle. So and we're going to do so by using the distance formula. So the first thing we have to do is we have to plot these points. So let's find minus 2 and 5. So there's minus 2, 1, 2, 3, 4, 5. So that's minus 2 and 5. I have to do it again. That's minus 2 and 5. The other is 12 and 3. So that's 5. There's 12. 1, 2, 3. And the other one is 10, which is there, and minus 11. You probably can't see that, but these 5 markers are slightly darker. So why did I bother to sketch it out? Well, I'm going to draw the resulting figure that way. And why did we do that? Because looking at it, you need to try to figure out which one is the longest side. So we're going to label, let me go ahead and label these points too. So this first point is m, which is minus 2 and 5. This point down here is n, and it's 12 and 3. And this point down here is q, and it's 10 and minus 11. So clearly the line segment between M and Q is going to be the hypotenuse. So this would be C, and we could say this side is A and this side is B. So this is actually a triangle if and only if A squared plus B squared is equal to C squared. But what is A? A is the distance between M and N, and we're going to square that. And what is B? It's the distance between N and Q, and it's going to be squared. And what is C? It's the distance between M and Q, and it's going to be squared. So let's find the distance. I find these easier just to find each one of these. This is my guiding equation. So I'm going to find each item in the left-hand side individually. Then I'll add them up and see if they're equal to the distance between MQ squared. But before we do that, I want to show you something. We have the formula. This is not as bad as it seems. We have the formula that the distance between P and Q is equal to the square root of the difference in their x values squared plus the difference in their y values squared. But this formula requires that we square that distance. So if I square this distance here, I have to square this here. And we get this beautiful thing that, for this particular problem anyway, that the distance between P, Q squared is equal to x1 minus x2 squared plus y1 minus y2 squared. So because these distances are squared, I don't have to worry about taking the square root. So we're actually going to use this little formula that was derived from our distance formula by squaring both sides. So let's first find out the distance between D, M, N. When M and M are points. So the distance between M and N is equal to the distance between their x values. So one x value is minus 2 and the other x value is 12. And that's going to be squared plus the difference in their y values. One y value is 5. The other value is 3 right there. And it's going to be squared. So that's equal to minus 2 minus 12 is minus 14. And 14 squared is here is going to be 196. I don't care if you use a calculator to find out what 14 squared is. And this you can surely do in your head. 5 minus 3 is 2, and 2 squared is 4. So the distance between M and N is, how nice, 200. So we've taken note of that. So let's do the next part. Just draw a little line there. The next thing I want to do is find the distance between N and Q squared. So the distance, that's not a good color for this. So the distance between N and Q squared is the difference in their x values. So here's N and Q. So it's 12 minus 10 squared, there's my 12, and there's my 10, plus 3 minus a minus 11 squared. One of the biggest problems in this particular, there's another parentheses in there, one of the biggest problems here is you will want to see, you'll see minus 11 is there, and this already has a negative in it, and you'll want to go off to the existing negative, and you can't do that. So 12 minus 10 is 2, and 2 squared is 4. 3 minus a minus 11 is 3 plus 11, which is 14, and 14 squared is 196. Oh, so the distances are the same. So whatever this is going to be, it's going to be an isosceles triangle. So now let's find, finally, the distance between M and Q squared. Well, it's equal to the difference in their x values, minus 2 minus 10 squared, plus the difference in their y values squared, 5 minus minus 11. Well, minus 2 minus 10 is 12, and 12 squared is 144. And 5 minus a minus 11 is 5 plus 11, that's 16, and 16 squared is 256. And the sum of those two is 400. So now let's go back, and we can verify it. The distance between M and M is 200, plus the difference between N and Q squared is 200, and that gives us 400, and that's exactly what the distance is between M and Q squared. So indeed, this is a right triangle. I want to go off on just a second. I know some of you don't, most of you don't know my background. You just know me because of these videos. You've not had a chance to talk to me, but I actually have 2 degrees. My first degree was in philosophy, and I taught that for many years. My first love was always mathematics, so I was the symbolic logic teacher. And then I got my second degree in computational and pure mathematics. And a philosophical question is the ability to look at something and judge something with your senses versus the organ of the intellect or with the mind. So I'm going to draw a line, that's not a line segment. Let me do this again. I'm going to draw a line segment. There we go. There. I'm going to draw another line segment. There. And then my final line segment is there. Now this sure as heck looks like a right triangle to me. I mean, if I look at it, I might actually take a protractor and put it on the screen, and it might very well look like that angle right there is 90 degrees. But it might be really, really close to 90 degrees, but not 90 degrees, like 90.00007. Mathematically, we can know exactly, by the method I just used in the organ of the intellect, rather than the organ of your eyeballs, we can determine, if we have the coordinates of A and B and C, we could determine if that was literally a right triangle or not. And I think that's pretty cool. So let's go on back. So here we have a new concept. So 2 or more distinct points are said to be collinear if they all lie on a straight line, and the distance between the first 2 points, so P and Q and R, is equal to the distance between P and R. And that's really, really easy to memorize. There's really nothing to it. So let's, that's not what I wanted to do. I want to draw a line. Let's draw a line. So I'm going to draw 3 points on this line. So here's a point here, a point here, and a point here. So I'm going to call this point P. I'm going to call this point Q. I'm going to call this point R. So suppose you see the line is drawn through there, right? Suppose the line was not drawn through there, but you know the coordinates, but you can't really see if they're actually on the line. Well, we know that they're collinear. That means they all three lie on the same line. We'll call this line 1. If the distance between P and Q plus the distance between Q and R, so notice they share that point right there, Q and Q, is equal to the distance between P and R. So that's the formula we're going to use to decide if 2 points are collinear. This again is just another application of the distance problem. In this one, however, we're going to have to take square roots because it's not the distance squared, but just the plain old distance. So let's look at the example given us, and we'll set it up and we'll work through it. So here's the point collinear theorem. 3 distinct points are collinear if IFF, that's not a typo, IFF is shorthand for if and only if. The sum of the distance between 2 pairs of points is equal to the distance between the remaining pair of points. So the best way to do it is just not even worry about who are the points, which one's first, second, and third, but just arbitrarily assign that. So here, what I'm going to do is, you can draw a line if you want, but of course we really don't know if they lie on the same line. That's what we're trying to find out. And of course, if you were to plot this, then they would probably look like they all lie on the same line. But if I were to way magnify in on here, I might find this little bitty point right here is just a scooch off. So I'm going to label this one as P, and it's going to have coordinates -1 and 5. I'm going to label the next one Q, and it's going to have coordinates 2 and -4. And we don't care if this is to scale. It doesn't matter. This is just a reference frame to help us get the formula right. And then the last one is going to be point R, and it's going to be 4 -10. That's its coordinates. So now we're going to use the distance formula. So remember, the distance between P and Q plus the distance between Q and R has to be equal to the distance between P and R. In other words, if I'm looking at this, what I'm actually considering is, I don't know what color to choose. I have choice paralysis, people. You ought to see me with Netflix or Prime. I can never decide what to watch, so I just give up in disgust. So this is the distance between P and Q, and I'm going to add it to the distance between Q and R. And clearly, if they're collinear, it's the same as the distance between P and R. So that's what's going on here. So let's see what mathematics tells us when we go to calculate this. So let's first find the distance between P and Q. So the distance between P and Q. Now unfortunately we're going to have to take a square root here. So the distance between P and Q, so I'm looking at these 2 points, is the difference in their x coordinates squared plus the difference in their y coordinates squared. So let's go ahead and figure out what that is. This is the square root of minus 1 minus 2 is minus 3. Minus 3 squared is 9. And 5 minus a minus 4 is the same as 5 plus 4, which is 9. And 9 squared is 81. So that's equal to the square root of 90. So now let's do another one. Change color. Let's do the distance between Q and R. Again, there's no getting around it. We have to use the radical. So it's the difference in, we're doing the difference between Q and R. It's the difference in their x coordinates. It's 2 minus 4 squared plus the difference in their y coordinates. Minus 4 minus a minus 10 squared. So that gives us the square root of 2 minus 4 is minus 2, but minus 2 squared is 4. Minus 4 minus a minus 10 is the same as 4 plus 10, and 4 plus 10 is 14, and 14 squared, what was 14 squared again? Let's just do it on the calculator, people. It's late at night. I don't know if you can tell that. I could just write it out, but I just want to. 196, yes. 196 plus 196. Literally, we just did it, didn't we? The last problem. My mind shot. So that's 200. So now we want to find the distance of P and R. So that's the difference in their x values squared, and then the difference in their y values, minus a minus 10, don't forget that, squared. And this is equal to minus 1 minus 4 is minus 5. Minus 5 squared is 25. 5 minus a minus 10 is 15. And 15 squared, yeah, I'm going to be lazy again. I'm sure you all don't care. And I'm actually fine if you do that, is 225. But I don't want decimals as roots. So that's the square root of 250. So here comes the hard part. We've got to add the square root of 90 plus the square root of 200. Well, how do we do this? And this is going to be some review. So this is the distance, and we want to see if it's going to be equal to the square root of 250. And I know exactly what you're going to do. You're going to grab a calculator, you're going to find out what that is, and then find out what that is, and add them together, and find out what this is. I probably can't stop you for doing it on a test. Well, let's do it. Let's try to do it without that. So notice that 90 is equal to 9 times 10, which is equal to 3 squared times 10. So I'm going to write 90 is 3 squared times 10. And 200 is equal to 10 times 20, which is equal to 2 times 10 times 10, which is equal to 2 times 100. So this is 2 times 10 squared, because 100 is 10 squared. So, and this is going to be equal to 25 times 10, which is equal to 25 times 10 is equal to 5 squared times 10. I'm not feeling good about this number right here. This 200 is not agreeing with my notes, and it's not agreeing here. Did I write down the points wrong? Minus 1 and 5, 2 and minus 4, 4 and minus 10. So let's indulge me here. Let's check this one, the distance between Q and R. I feel like I've done something wrong. So here is my Q, and here's my R. So 2 minus 4 is correct, and minus 4 minus a minus 10 is minus 4, right there, yes. I took that as this is minus 4 plus 10. So this is indeed wrong. I apologize. Again, the point is you correct yourself. So minus 4 plus 10 is 10 minus 4, which is 6, and I'm going to square that. So I'm getting, the 14 was right too, because it sounded right, because we just did it. So that's going to be the square root of 40. Sorry. If some of you saw that and you were waiting for me to correct it, I normally do. That's the reason I work the problems out beforehand, is when you're talking and pointing and moving, things can happen. So let's go ahead and change this down here. This is going to be the square root of 40. Much, much better. Go ahead and erase this. So these are pretty much interesting applications, and they are not trivial. Statistics, so much of applied mathematics that you use all the time will at the basis use these types of things. So we're not going to do 200 anymore. Let's go ahead and erase that, but let me, being lazy here. So this is 40, and that's equal to 4 times 10, which is equal to 2 squared times 10. There we go. 2 squared times 10. And finally, we never finished that last bit. 25 is 5 squared times 10. So I'm going to go ahead and write 25 as 250 as, I didn't have to erase the 10, 5 squared times 10. Now the nice thing about this is, since this is squared, I can remove it from underneath the radical. I mean, the exponent is even, and the index of the radical is 2. So I divide the exponent by 2 and I get 1, and it allows me to move 3 raised to the 2 divided by 2, which is 3 to the 1, out from underneath. And that's 10. Over here, the 2 squared can move out. The square root of 2 squared is 2, and that's multiplied by 10. And over here, the square root of 5 squared is 5, so it moves out, but the 10 stays under. So now I have like radicals. So like radicals, again, are radicals that have the exact same number underneath the radical symbol, and the radical has the same index. So 3 times the square root of 10 plus 2 times the square root of 10 is 5 on the square root of 10. And indeed, that is equal to 5 on the square root of 10. So we were able to discover that those points were collinear without doing any decimal conversion. And I kind of know that's how the problems are going to work out, because they want you to practice adding like radicals. So here let's look at another concept that's going to be important. So here's a line segment, and again I'm going to put 2 points on it. 1 point here, which I will call P, and it will have x1 and x2, not x2, sorry, x1 and y1. And here at the very end is the other point Q, and it has coordinates x2, y2. So suppose I really need to know and find the coordinates to a point that is in the dead center. Say right here. What are the coordinates of this point? So this point is called the midpoint. Why? Because the distance between P1 and we'll call this point R, and the distance between R and Q are identical. But here is the beautiful part about it. We don't have to use the distance formula to find R, or these distances, no square roots at all. So the midpoint, so if P x1, y1 and Q x2, y2 are 2 points, then the midpoint, and the book is using instead of R, they've got it labeled M, so let's just go ahead and be consistent. So the midpoint M has the following coordinates. So this is a point. So M is a point. So what you do is you add both of the x coordinates and you divide it by 2, and that gives you the first slot of the ordered pair that denotes the location of M. And guess what? You do the same thing with the y coordinates. And now I know the coordinates of the midpoint x3. The midpoint M. So that would be x3 and y3. x3 would be x1 plus x2. You don't have to think about that. But these are the coordinates of the midpoint between P and Q. So let's go ahead and do an applied problem, a hamburger problem. So here we have a graph. The following figure depicts how a graph might indicate the increase in the revenue generated by fast food restaurants in the U.S. from $6,938 billion in 1990 to $195.1 billion in 2014. Can you imagine? That's their revenue. Of course, it's all of the fast food restaurants in the U.S. That's just the freaking U.S. We pay a lot of money to go to McDonald's, huh? Use the midpoint formula and the 2 points given to estimate the revenue from fast food restaurants in 2020. and compare it to the actual figure. So what we're going to do is we're going to just look at points. So this point here, I'm going to call P. It has coordinates. What is my x value? 1990 and 69.8. That's billion. And this point up here, I'm going to call it Q, is equal to 2014 and 195.1 billion. So they want us to find the midpoint of the two. So the midpoint in the two is going to be found by you add the x coordinates and you divide them by 2. Remember, the midpoint is a point. And you add the y coordinates it's supposed to be at 0.1, people, and you divide it by 2, and now it's just simplification. So this is going to turn out to be, I've done the math for you, this is going to be 2002, and that's the exact year that they wanted to know about, and this turns out to be 132.5 billion. So they said compare it to the actual number. The actual number is 138.3 billion. So 132.5, 100 versus 138.3, that's 5.85 billion off. So what that tells us is that the cells is not exactly linear, that it can be approximated by a linear graph, but it's not quite linear. If it were linear, it would be perfect. So an equation in two variables is a mathematical statement that equates two expressions where two unknowns, which are variables, appear in the equation. Those unknowns are almost always going to be x and y. Here's an example. 5x minus 7 is equal to 2y plus 3. So we will assume these two variables are x and y. I already said that. Hence a pair of x together with the value of y, hence a value of x together with the value of y that makes the equation true is said to be a single ordered pair solution. Most of these equations have infinite number of solutions, and an ordered pair xy, where x is an actual number and y is a known number, if you plug them in and it makes a true equation, then that's an ordered pair solution. As far as the visual graph goes, we could plot that point. He would say that point lies on the graph of that equation. So in the above case, we can verify that if xy is equal to 0, 5 are values that make the equation true. So let's plug in 0 for x. So 5 times 0 minus 7 gives me minus 7. And 2 times minus 5 is minus 10. Plus 3 is minus 7. So this is a ordered pair solution to this equation, mathematically. Visually, the point located on the rectangular coordinate system by 0 minus 5 would lie on the graph of that equation. And the graph of the equation is the totality of all points x, y, which are solutions to the equation in two variables. So for this, we want to find at least 3 ordered pairs that are solutions. So here is really the only way to do this. We make a table of values. So you've seen this before. You should have seen this before in plotting. But I have y is equal to 4x minus 1. So what I want to do is make a table of values. They say we want 3, so that's fine. So what you do is you make a table, and we're going to have the column headers, which are going to be x, y, in 3 rows. So this is going to be x, and this is going to be y. So the cool thing about it is you get to choose one of these, and if you choose one, you use that value to calculate the other. And I always find it's really easy to always choose a 0x and then a 0y and some easy number for x. So let's go in. So this first row says let x be equal to 0. So y is equal to 4 times 0 minus 1, which is minus 1. So I discovered minus 1. The ordered pair solution is 0 minus 1. Because x is 0, y is minus 1. So for the second go, again we have y is equal to 4x minus 1. This time I'm going to make y be equal to 0 and solve for x. So 0 is equal to 4x minus 1. I'm going to move the minus 1 to the other side and change its sign. So I'm just solving an easy linear equation. Now I'm going to divide both sides by 4. So 1/4 is equal to x. So I assumed y was 0, and I derived that x was 1/4. So that gives me another ordered pair solution, 1/4 and 0. And then for the third, I chose, so you have to choose one, and I said let's just choose x to be equal to 1. So choosing x is equal to 1, we have y is equal to 4x minus 1. Well, 4 times 1 is 4, so that's 4 minus 1, which is equal to 3. So I derived 3. So I have 3 points that are ordered pair solutions to equation A. Now your points may be different. How would I check them? I would plug in your values into the original equation to see if they actually turn out to be an original equation. I mean, a true statement, a true equation. Now here, the next one, for B, we're going to want to, again, we're going to make our table, but B is x is equal to, remember, this is the positive root of y minus 1. So here are the thing. Here is the thing. For the rectangular coordinate system that we're doing, all values of x and y must be real numbers. That means no complex numbers at all. No a plus bi where b is not equal to 0. None of that. These are all going to be real numbers. So that observation right here already kind of restricts some of the numbers that I can plug in for y. And here usually, if you have, so I can't use y is equal to 0, because then I would have x is equal to the square root of minus 1, x is equal to I, and that's not allowed. So here what we want are numbers of our values for y that make y minus 1 greater than or equal to 0, because the square root has to be greater than or equal to 0 for x to be a real number. So let's choose clearly 1. So that tells us y is greater than or equal to 1. Let's just do 1. And I want to be able to plot this, so I'm going to choose 5, and then I'm going to choose 10. Let's see if you can figure out why I chose 1, 5, and 10. So let's do the first one. So I've chosen 1, 5, and 10. So the square root of 1 minus 1 is the square root of 0, which is equal to 0. So I discovered that x is equal to 0, and I have one ordered pair solution, 0 and 1. Now I've chosen that y is equal to 5. So x is equal to the square root of 5 minus 1, which is equal to the square root of 4, which is equal to 2. I wanted that to be a perfect square. So I got 2 and 5 is an answer. And finally, I chose 10. I hope you now understand why I chose 10. X is equal to the square root. Y was chosen to be 10. 10 minus 1 is 9. The square root of 9 is 3. So I have the points 3 and 10. Over here, I'm not going to do this next one. You would do the exact same thing. You would make a table of values just like I've done, and you would use that table of values to find as many ordered pair solutions as you want. And of course, the next thing it's going to do is it's going to want us to graph them. So all I'm going to do is just graph 3 points here. X, I'm going to do the 3 points that I got for y and the 3 points I got for x. So what I need to do is write those down really fast. I haven't got them written down. And then we'll actually do it in GeoGebra actually. So let's write them down. I'm still going to have to write them down. So my first one, seriously? Okay, it's working now. So my first is 0 minus 1, 1/4, and 0, and 1 and 3. I probably have them on my next page. I actually have several more. And then that was y is equal to 4x minus 1. And then I have 0 and 1. Two and 5, and 3 and 10 for x is equal to the square root of y minus 1. And then we will actually look at y is equal to x squared minus 4. Okay. So let's go to GeoGebra. And I will start anew. What I'm going to do is I'm going to plot the point y is equal to 4x minus 1. And our first point was 0 and minus 1. And there it is. My next point is 1/4. And you have to be careful here where the comma goes. And 0. So there is that one. And my next point is 1 and 3. So let's actually do something here. If I draw a line between these 2 points, then when I type in my next point, it should lie on it. So my next point is 1 and 3. And indeed it does. So that is the graph of y is equal to 4x minus 1. Well, let's maybe just do, now let's just go ahead and start all over with a brand new graph. And for this case, I have 0 and 1, 0 comma 1, there that is, 2 comma 5, there is another, and the next one is 3 comma 10. I actually could do another one, 4 comma 17. So you can't see them, can you? And a next one would be 5 comma 26. And let's see what's going on. So let's actually see what the plot is. X is equal to y minus 1 raised to the 0.5. Yeah, and right there you go. You can see clearly that the points we did fit the actual graph quite nicely. We didn't actually graph any points for the last one, but we did take note of its equation, and its equation is y is equal to x squared minus 4. And I hope most of you were expecting a parabola, and that's exactly what you got. So what else do we have for this? Is that it? Yeah, let's do one other mathematical reasoning. So I'm going to talk to you about a very important concept here. It's called conditional statements. They are the heart of mathematics. So a conditional statement is a statement in the form if P then Q, where P and Q are themselves other statements. For example, if it rains, then the river will overflow. In this case, P is it rains, and Q is the river will overflow. Given a conditional statement, if P then Q, the converse is if Q then P. In the above case, the converse would be if the river overflows, then it rained. In many cases, a conditional statement can be true, whereas the converse is not true. It might very well be true if it rains, then the river overflows, but it may not be the case if the river overflows, then it rains, because the river could overflow for other reasons beside it raining. The river could overflow because a dam upstream broke. So, however, some cases, it's always true. If a conditional statement is true, means its converse is also true, then we call that statement an equivalence. And we no longer state, and we can say the following: P if and only if Q, which means if P then Q implies if Q then P. But we don't say that, we just say P if and only if Q. Or we just write P IF Q. That's not a typo. That means if and only if. These are really powerful statements. So here is a challenge for you. And what I'll probably do with this is make it a bonus or an extra credit. I won't put it on the exam. Find an example of a conditional mathematical statement, not one about rivers and streams. A conditional mathematical statement. So it's going to be in the form if P then Q, if x squared is, for example, state its converse. So if P then Q, then if Q then P. So you just give a statement, then write its converse. And then find an example of a conditional mathematical statement whose converse is always true whenever the conditional statement is true. This drove some of my college algebra students to distraction, which is really unfortunate. The two that were, some of the ones that were most bothered by it were the ones that could do algebraic manipulations just perfect. But when it came to mathematical reasoning, they locked up. And that's terribly, terribly sad, because mathematical reasoning is the engine that drives math. So for this, I give you a hint. Let the statement P be two ordered pairs are equal, and let Q be the value of the x coordinates are equal. So the conditional statement would be if two ordered pairs are equal, then the value of the x coordinates are equal. So its converse would be if the value of the x coordinates are equal, then the two ordered pairs are equal. So right there I give you A and B right there. However, finding C, an example of a conditional mathematical statement whose converse is always true whenever the conditional statement is true, will be a little bit more difficult. Anyway, I can't really tell if this was a long lecture or not. There was a lot of things, but notice we broke them all down into little steps, and in doing so, we were able to conquer them.